So let's continue to talk. So anything you gotta know before the weekend about the quiz? Anything that's gonna keep you awake forever? Yeah.
When you do the problem, prove 10 people in the room has 2 people same day.
Oh, prove that 2 people are born on the same day? So that's the pigeonhole principle. Okay, so make 7 buckets labeled Monday, Tuesday, Wednesday, Thursday, right? And put each person in a bucket based on the day of the week they were born. If you have more than 7 people, at least one bucket will have at least 2 people in it. And those 2 people must be born on the same day, because that's why they're in the same bucket. So that one you can almost kind of wave your hand and say pigeonhole principle.
So I do with a week where there has 7 days.
Mm-hmm.
Then I only 2 people have 7 days, so I just 7 minus 1 equals 6 days. We got 6 days for all the 8 people.
Okay.
Then just 1 day for 2 people.
Sounds like it's in there.
Yeah.
Yeah, I'll take a look at it.
Is there like a formalized version of it? Like if we are asked to prove something using the pigeonhole principle on an exam, is there like a formalized way to do it, or can you just talk about like, all right, using the pigeonhole principle, we have this.
So you could so as long as you describe, okay, let's have 7 bins labeled on the day of the week, put people in there based on the day of the week. By the pigeonhole principle, since we have 10 people and 7 bins, at least 1 bin will have at least 2 people in it. Those people will therefore have been born on the same day of the week.
Okay.
Something like that.
All right.
I'm really curious to see which 2 questions most people skipped. That one, yeah.
Pascal's triangle.
Yeah, I was gonna say.
Pascal's triangle? Really?
That's one I did.
If you know it, it's easy, but if you don't know it, then...
Can you go over that one?
Yeah, what was the question?
It just looked complicated, so I
it
just
was-
threw it right out.
Yeah, I
What's
know.
the significance about 20 in terms of?
Permutations and combinations, right?
So what's significant about the 20?
Yeah.
So remember, each element in here is a combination, right? So this is C0, this is C, this is 0, 0. This row is 0, 1, and, sorry, 1, 0, 1, 1. And this row is 2, 0, 2, 1, 2, 2, and so on. So 3, 4, 5, 6. So this row is 6, 0, 6, 1, 6, 2, and so on. So that 20 right there is actually 6, choose 3.
Okay, so if we just wrote combination 6, 3, then we
That's the
got
significant,
it.
yeah.
I just started guessing and checking from 6, 6. And
Okay.
I'm decrementing the.
And you got the
choose
3 and it
one.
worked
I
out?
got 20,
Okay,
so I was like,
yeah.
This is probably right.
Okay, yeah, it is. Yeah, so every number in there is the result of some combination. So something, choose something.
I haven't done that since like middle school.
Cool. So we were going over the homework on Wednesday, and we were looking at that question about 8 letters of the alphabet and how many words can you form, and there's 2 ways to interpret it. And when we got to, if you're not allowed repetitions, the order is important, so it's a permutation. But if you're allowed repetition, I said you go back to just the basic product rule, and it's 26 times 26 times 26, so it's 26 to the 10th. And somebody said something about how you have to throw away some of those because the order of the letters that are the same doesn't matter. But that's not true. I bought into it for a moment there, but it's not true. If you have an 8-letter word, right, the number of ways you can pick the first letter is 26, number of ways to pick the second letter is 26, and so on. It's still just 26 to the 10th. And that's not treating, AA something as different from, AA where you swap those, because that's not how we're forming these things, right? We're picking an A and then we're picking a second letter and so on. So it's going to be 26 to the 10th if you pay attention to, if you allow redundancy, and that doesn't get tripped up by order. And you can think about that with digits. right? That's how we got the number of 3-digit numbers was 1,000. It's 10 cubed. Even though your number might contain the same digit more than once, that's okay. So I don't know why I believed that comment, but all right. So we're talking about languages, and we mentioned briefly on Wednesday that there's different ways to describe what's covered by a language, right? One way is to have a dictionary that lists all the things that are valid. Another way is to come up with some requirements for something to be part of your language. A third way is to come up with rules for producing things that belong to your language. Okay, and that's what we're going to talk about today, is something called a phrase structure grammar. It's a way to produce words or sentences that are valid in your language. So let me throw some definitions at you. And we're just going to use these. So a vocabulary, V, is a finite, non-empty set of symbols and these are words that we use all the time, so we've got specific meanings in this context. So I'm going to try to be clear about these. So vocabulary V is a finite, non-empty set of symbols. Okay, we can use the terms word or sentence. So a word or a sentence over V is basically a finite length collection of elements of V. So it's a finite length string. A finite length string comprised of elements of V. So V is our vocabulary, that's a set of symbols. A sentence or a word over V is just a collection of those strung together side by side. So we use the symbol lambda to be the empty string. So it's a string whose length is 0. It contains no symbols. So this is the empty string. Or it could be the null string. And don't confuse that with the empty set. Okay, a set is a totally different thing. These are strings we're talking about. So they're just collections of symbols. But lambda is the collection of symbols that has no symbols in it. So it's just, quote, quote, nothing in between. Okay, V with an asterisk on top. This is a set, and it's the set of all words over V. So that's the collection of all strings of finite length comprised of elements of V. That's the same star you get in regular expressions, by the way. Okay, so here's the definition we're after. So a language over V is a particular subset of V star. Bless you. So when we talk about a language over vocabulary, we're talking about a specific collection of finite length strings made up of symbols from that vocabulary. So for English, think of the vocabulary as being the letters A through Z. A word over V is just a collection of letters strung side by side. V star is the collection of all finite length words, right? So pick 1,000,000 letters and string them together, you've got something in V star. But then a language is a subset of V star. So we could describe the English language as those words that we choose from the set of all strings that we consider to be part of this language. Or we could have a language of, the Swedish chef, and it would have a different set of words. All right, so that's our setup. So a grammar, I'm not going to define that. I'm just going to show you our object of study. So we're going to work with a phrase structure grammar. So a phrase structure grammar, G is a four-tuple comprised of V, T, S, and P. Where V is a vocabulary. T is a set of terminal symbols. And so T is a subset of V. It's a collection of a few particular things from our vocabulary. S is a start symbol. So that's something inside our vocabulary. And P, this is the fun part, P is a set of what we call productions. And productions are ways to take one word and turn it into another word. So the ways we can transform things. And that's all horribly abstract. So let's do some examples. So we're going to describe a grammar, V, T, S, and P. V is going to be the following set. So little a, little b, big A, big B, and R. My terminal symbols are going to be little a and little b. My start symbol is going to be the symbol R. And my set of productions are going to be as follows. So R can be turned into big A, big B, little a. A can be changed into, big A can be changed into two uppercase B's. Uppercase B can be changed into lowercase ab, and uppercase AB can be changed into B. So here's the idea. If we start from our start symbol R, we can apply any of these production rules if the left side matches R. So R is our start symbol. R can be replaced with, so let me do it like this. So here's an R. R can be replaced with a big A followed by a big B followed by a little a. Our goal is to apply these production rules and eventually come up with something comprised only of terminal symbols. So a big A could be replaced by an uppercase B and an uppercase B. And this uppercase B right here could be replaced by a little a and a little b. And an uppercase B could be replaced by a little a little b. And so by applying those particular production rules in this order, I've taken my start symbol R and I've changed it into the string AB, 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 A. Any other way I could have started from my start symbol R and turned this into something comprised of terminal symbols?
Probably converted the set AB into just B.
Okay, so I can still take R and turn it into ABA, but we have a rule that says AB can be replaced with a lowercase b. And so now from my start symbol I've created the string little b, little a, comprised of terminal symbols. So that's another part of our language.
Would that mean that the two sentences or a statements strings are equivalent then?
It means they're both valid. So our goal here is to identify collections of terminal symbols that are part of our language, right? And anything that we can derive starting from our start symbol using these production rules will be part of our language. That's the whole thing we're trying to do with a phrase structure grammar. So we found two things that are part of our language. This string here, AB, AB, ABA, and this string BA. And I believe those are the only two we'll find. But depending on how we change the production rules and what we start with and what our symbols are, we can come up with descriptions of all kinds of different languages. And these rules are kind of saying, if you kind of think of it as like diagramming sentences a little, so our start symbol might be a sentence. And this might say a sentence is an article followed by a noun followed by a verb. Or a noun phrase followed by a verb phrase. And a noun phrase could be an adjective followed by a noun, or it could just be a noun. And so these are sort of describing possibilities for how we can expand from a starting point.
Are those retraceable? So if you gave us just a string AB, 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 A, can we grab those and then say, well, AB is equal to B?
I think in this case we can, but not always. Right? There could be multiple ways to get to the same word. Okay, so let's formalize this, and then we'll start playing with some examples. So these are definitions. So let some W0 equals some left-hand piece, some middle piece, and some right-hand piece. So this is a string that we can think of as some substring L, some other middle string Z0, some other string R. And suppose there's another string W1, which has got the same stuff on the left, some different piece in the middle, and the same stuff on the right. Okay, if there's a rule which says Z0 can change into Z1, if that's in our set of production rules, then we can say the following. We can say W1 is directly derivable from W0. So W0 looks like this first form, W1 looks like this form. If there's a production rule in P that says Z0 can be replaced with Z1, then the second expression is directly derivable. And that's what we're doing in here. We're saying, well, B could be replaced with AB, right? So a single production rule means W1 comes from W0, and we can write this as W0 and then a double arrow W1. So that's a definition. Here's another definition. So if W1 is directly derivable from W0, and W2 is directly derivable from W1, and so on, up through Wn, which was directly derivable from Wn minus 1, then we say Wn is derivable from W0. So it's not directly derivable. There's no single production rule, but we can change one thing into another, and eventually get it into Wn. So Wn is derivable from W0, and we write that as follows. It's an arrow with a star on top. Yeah. So just looking at this derivation that we did over here, we can conclude that if we know BB, from that we can directly derive little a, little b, uppercase B. Right, because there's a single production rule that lets us replace B with AB.
And then you could do big V, little a, little b.
Mm-hmm. And if we do multiple productions, right, this string is derivable from that original string. And in fact, that final string is derivable from our original starting symbol, R.
So then every string would be derivable from the starting symbol.
So every string is derivable from the starting symbol. And that's our definition of language. So here's the definition we'll work with for the rest of this. So definition. The language generated by G and we can write that as L of G equals a set of strings of terminal symbols that are derivable from the start symbol. Equals the set of all words W contained in T star. Remember, T star is the set of all words over that vocabulary of terminal symbols, such that we can get from S to W. So there's the fancy schmancy definition of the language generated by a phrase structure grammar. It's a set of all words in the comprised of terminal symbols that can be derived from the start symbol. All right, so let's try some more examples. So our vocabulary is our start symbol, a 0 and a 1. Our set of terminal symbols are just 0 and 1. Our start symbol is R. And our set of production rules are as follows. So S can be replaced with 1, 1, S, or S can be replaced with 0. And we want to find what the language is generated by that. So what kinds of things do you think are in this language?
Binary numbers,
Which kind of binary numbers? You're right, binary numbers.
3-bit binary numbers.
3-bit binary numbers. Any 3-bit?
You can also have 4, 5.
Even ones?
Even ones?
Yeah, you could only have even ones. They'd have to end in a 0.
Got to end in a 0. Anything else?
They have to start with 2 ones,
Have to start with 2 ones.
and that's it.
So there's no hard and fast algorithm we can use to answer these questions, okay? This is going to be an exercise in sort of playing with these and trying to get a feel for what you get with different types of production rules. And this is the analysis part. We're starting with a grammar and we're exploring it to see what kind of things are valid over that grammar. And then later on, we're going to switch to synthesis, and we're going to say, okay, if we want to write a grammar to represent something, what should the production rules be, what should the start symbol be, and so on. So we'll switch to a synthesis thing, as with most things we do in the curriculum. But we begin with analysis. So how can we sort of rigorously figure out everything that's in the language? We could start doing derivations, right? So, okay, were you going to say derivation?
Yeah, I was just gonna say just keep trying to brute force and
Okay, so we're going to start with our start symbol S, which is R. And let me write this differently. Okay, that's what I meant. Okay, so what can we turn R into?
Could R be like just 1, like infinitely? Like just 1, 1, 1, 1, 1, 1?
So we got to have finite length strings.
Okay.
And that's where that kicks in.
so you could turn into 1, 1, 0.
Okay, so this could turn into 1, 1, R, and R can be replaced with a 0. So there's a 1, 1, 0. That's definitely part of our language.
And then 1, 1, 1, 1, 0.
1, 1, 1, 1, 0, because R could become a 1, 1 followed by an R, and R could be a 1, 1 followed by an R, and R could be a 0. So that's part of our language. But it could also be a 0, because if R is our starting symbol, we've got a rule that turns that into a 0. And that's probably it. So it's any string comprised of an even number of ones followed by a 0. And 0 is an even number, so this is an even number of ones. It's no ones followed by a 0. Got that? We got 5 minutes. So try this. Go ahead and grab a spot on the board. Do this in groups. All right, you got 5 production rules.
Dude, dishes.
Show up on the video and just like, go to the board and you just hear he works faster if you punch him.
I gotta do this.
0, 1, and
Right, start writing things.
You have to finish the sentences everybody.
S
Go.
is equal to R.
Traveler sandwiches.
T is 0 and 1.
Okay, so what are we? How do you even start? R.
P.
Start with R. Okay. Okay, so
We got
R could be 0
0,
A could be
R can be
A.
turned into 1 and 0 B.
No.
A can
0
be turned into 0 and
B
B.
could be. I don't like this. And then A can be 0B. And then B can be 1A. A can be 0. Okay. Look.
Yeah, B could be 1.
No, you can make it whatever you want. It's your rule.
Minecraft? No one can tell you what to do. You are the boss of your world. You're wrong. No, you. No, you.
Wait, now hold on. Now hold on. Okay. Now, wait. Last time we had R can go to 1, 1, R, right? And that's how we made it from 1, 1, R to 1, 1, 0. Or
No, the 1, 1, R.
no, because we're replacing R with 0. So it would be 1, 1, R, 0. That becomes
No.
So my point being. So now we can work with these.
The thing is, it can be infinite. You can have
0. Yeah.
Always wanted to do more work. I did more work.
Start with the
0, 1, 0. And that could be 0, 1. No, this is the farthest you can take. A can be 0, B can be 1. A can be 0, B.
Well, you don't add a 1 there.
1A.
I
You
know.
replace the A.
No, but you don't take 1A to be that because only A is equal to that. Yes.
So regardless of how it.
There is.
Okay. So we have 0A. B can be 0, 0, B. So,
Or well.
0, B. And B can become 0, 0, 1. Or it can go 0,
Oh, 0. I forgot that there's a
also.
count.
So the second is always going to be 0.
So that gives us 4 patterns. And these patterns don't repeat. So we can have 1, 0, 1. We have 0, 0, 1.
The second is
And we
always
can have 0,
because there's always going to be 0.
this section.
The second is always there.
Would they be just 0, 1, 0, 1?
So once we get to this point, you can actually never go here. So 0, 0, 1, 0. Only 0, That's the only time you never hit 0. So 0,
So you're saying you're defining R. You're deriving it.
So then that agrees to modify.
Well, that's what we're doing. R can be defined
Then if you have this B,
So I guess we can also have. No, this is still just a base form. Unless we all.
Because it's always gonna have this, so it's always 1, 0, 0, 1, and then you have the choice of turning where A equals 0, and then B
So now our
is way to be
only. These are the ones that can go on indefinitely.
Well, that also always alternate. Well, that also means that they're always going to have. No, it's just. We can ask them. They have to start with the numbers always.
these are all
And
then after that, I think it's gonna be 0, 1, 0. The number actually has to always get that. So the second number also has to be like whatever.
No, I mean, that's as far as I can tell, everything was good. I don't know what to do with
All right, so we're out of time here, so play around with this a little if you'd like. We'll go over this again on Monday, but I think everybody's got this. We'll look at how we can express this in general. All right, so have a great weekend. Watch out for the crazy snow that's coming down right now. I'll see you next